Hello everyone, welcome to the fifth lecture on deep learning, where we're going to be studying deep generative models. So in this lecture we're going to define generative models and discuss various different examples of them. Then we're going to look at the theory behind simple density estimators and look at the relationship between density estimation and generative modeling. Specifically we're going to be looking at the maximum likelihood approach and the derivative divergence measures. And then we're going to look at sort of how we sample generative models, how we create new examples, create new data, which follows and models the data distribution. We'll be examining some of the main issues with just the sort of naive autoencoder based strategies, but we won't really be going into generative adversarial networks, because we'll cover those in more detail in the following lectures, in the next lecture in particular. So by the end of this lecture you should know the foundations to build a deep generative model and the theoretical issues in actually designing them. So in future lectures we're going to be looking at sort of state-of-the-art generative models that build on these foundations that we will introduce today. So just a kind of quick recap from the previous lecture, we discussed that we can taxonomize learning into three classes. We have the probability of y conditional on x, which was the discriminative modeling, such as classification tasks. Then we had the probability of x conditional on y, which was our conditional generative modeling, like where we had time series forecasting, predicting the weather, given the previous week's sensory data, predicting faces, conditional on age and gender, and so on. And then we talked about how actually the sort of larger problem is the problem of modeling the joint distribution, or modeling the probability of x and y. And this is really the core of generative modeling. So estimating the joint distribution of the data and trying to do that in an unsupervised fashion. For example, if we're given a data set containing images of the stars, can we learn how to fully generate it? Then if we've done that, we've somehow learned all of the rules of physics and so on. So what is it? Let's just sort of look at a definition and zoom in on generative models. The definition is that it's just a model that learns the joint distribution over the entire data set. And that means we can do one of two main applications. We can generate new examples by sampling from the model. So we can perhaps give the model some inputs like a normal distribution or some uniform distribution, and then we can sample the model at that distribution and synthesize new examples. Or we can actually sample from real data and we can evaluate the likelihood of that data, which tells us the probability of the data. And in some cases you might have this as like an invertible function where you can actually go from some likelihood and go back to the original data. So we call this like the sampling problem, where we sample some new data of some dimension from the model, so sampled from the model, and then the other one is just estimating the likelihood of the data. How probable is this kitten, or how probable is this dog? What is the probability of it having occurred in the actual data that this model was trained on? So this is the density estimation problem, and this is the sampling problem. And some more examples we might say, like, is this just, we've just been looking at images so far, but is this just be restricted to images? Well, actually no, we can just talk about this as being any signal. So linguists might be interested in modeling the probability of a sentence. So what is the probability of the sentence? You might have a sentence like, the dog chased after the ball. That's quite a likely sentence. We would expect to see that on the internet or in a given sentence in a conversation. Whereas the sentence, printers eat avocados when sad, that's just a nonsensical, meaningless sentence. It's very, very unlikely that you would encounter that sentence on the internet or in a conversation. So we often try to learn some distribution over the next tokens in a sentence, and we try to estimate the likelihood of that. So the cat sat under, and then what is the next most likely, or the distribution over the next most likely tokens? The floor, the rug, the carpet. They're all likely outcomes, but the cat sat on the suction type 5 Stirling engine is an unlikely outcome, so that would have a low probability associated with it. Meteorologists, they might be interested in the probability of whether it will rain, so you could add the probability of rainfall. You could also have that as a conditional generative model, so what is the probability of the rain conditional on some state being in the Sahara Desert, whereas you might have what is the probability of rainfall conditional on some state being in North Durham, in which case you would have quite a high probability. Artists might be interested in the probability of an image being a face, so what is the probability of this painting being a face, or what is the probability of this photograph containing a face. And whereas musicians might be interested in the sound, or what is the probability this piece of music sounds like Beethoven, probability of Beethoven. So one of the main ways we do this is by the maximum likelihood equations. And the maximum likelihood equations really is an optimal way to fit some distribution to our data. So let's just say we've got a normal distribution which is parameterized by mu and sigma. We want to somehow adjust the parameters of mu and sigma to optimally fit to the observed data under it. So I'm going to just show this in an example in the notes. So if I bring this down, swap over to the notes here, I'm just going to write down the definition for our function that we want to, or our distribution that we want to maximize the likelihood of the parameters over our observables. So let's just start by writing down the probability of a model is equal to some normal distribution which we're going to parameterize. It could be parameterized by theta as in the slides, or by, which could be any number of parameters, but in our case we've just got two parameters. We've got nu and sigma, and these are the parameters we want to optimize. And then we just get the definition of the normal distribution function, which is just 1 over sigma. This is just our normalizing constant. This ensures it integrates to 1 times exp of minus 0.5. And then we've got x minus mu, so this is our translation on the x-axis, over sigma. We're going to square that. So that's the definition of a normal distribution. And what we want to do is we want to find these parameters here, or find the values of the parameters that maximize the likelihood over our observed data such that it's most probable. So let's just show an example of some data. So I'm just going to plot some data drawn from a normal distribution. So there's lots of samples near the mode, maybe a couple of samples near the tails of the distribution. And let's just start off with an initial estimate of, well, just some random parameters of mu and sigma. Let's just put our distribution over here for now, which is clearly in a bad place. It should be over here. So how do we actually move mu? This is our mu. How do we actually know what the best value of mu is? Well, we use the maximum likelihood equation. So what we do is we basically take up, we multiply, or we evaluate the probability, I should say, of the function being here by our data. So you can see if we sample this at the y-axis of the probability, it will be, this is all very low. So let's just plot what this looks like in another sort of graph over here. This is for mu. And just imagine we kind of slide this function this way, and let's just plot these results. So what we're going to get is we're going to get, for this place here, it will be very low, and then as it slides over, the product of all the probabilities is going to increase, and then it's going to decrease again. And then what we do is we say that the maximum value of this function here is where our mu should be, which corresponds to here, which means that the maximum likelihood in this case is here. So we also do the same thing for the other parameters. So we actually maximize the likelihood over all parameters, but just to show this for the standard deviations, what it would look like. Again, we have some data drawn from our normal distribution. And now just imagine we change the sigma parameter and we plot the different values for sigma up here. So you could imagine like a very sharp sigma, and then we could flatten it, and if we change it, then you'll get this range of values. And as you plot sigma, again, you'll find there's some value for sigma, which probably corresponds to something like this distribution here, where the likelihood is maximized. So if you were to do this, like, and plot like both of these values for sigma in some space, you could sort of, so if you've got like mu and sigma, you can imagine there's like some function where the maximum of this function corresponds to the optimal values for mu and sigma. Okay. move that back. So in practice, this is often quite inconvenient using this product here, because the product itself is prone to numerical underflow. So if we observe if you remember the log rule from when you last studied maths, if you recall that the product rule for logarithms is that if you take log of x times y, that's equivalent to doing log of x plus log of y. And we observe that taking the logarithm of the likelihood doesn't actually change the argmax, it doesn't change the maximum. So therefore we can conveniently change that product into a more convenient sum. So as in the last lecture, we can't do this over the entire data distribution. So instead what we do is we tend to do this empirical estimate. So we, just from the observations x sampled from the data, so we do this kind of expectation over it. So you may be asking yourself, well, that's great, we can now fit our distribution to our data, but how do we actually, why is that a generative model? How do we actually sample from that distribution? So what we can actually do is we can parameterize the model. If we can derive the cumulative distribution function, which is basically the antiderivative of the probability density function, the p model of x. And by the way, the antiderivative means that the derivative of the CDF is the underlying probability density function, the normal distribution. Then we can actually use the CDF to sample from the model. So I'll show this with a 1D illustration again in the notes to make it clear. So let's just say, let's first of all just draw what the CDF is by its definition. So if we've got our normal distribution here, so I'll just again show our model. This could actually be like a deep neural network, but I'm just showing it as a normal distribution parameterized by mu and theta. Sorry, it's a terrible looking normal distribution, but it will do. Now I'm going to just show you what the CDF is. So basically, if we sort of integrate along the x-axis, so we plot the results here. So we sort of compute that integral, then compute that integral, and keep integrating alongwards and plot. We end up with the CDF, which is a monotonically increasing function, which looks like this. So it usually looks something like a sigmoid, and it goes on and on. And so we call this f of x. Now, if we've computed this, we can actually sample from it. You might be wondering, well, how do we do that? Well, what you can simply do is you can simply take a uniform distribution. So here's a uniform distribution between 0 and 1. We would say these are samples from our uniform distribution. So you would get nice regular sampling here. And if we find where these samples intercept on the y-axis, you'll see we've got nice uniform samples coming across this way. We can then project our samples from this uniform distribution via the cumulative density function, the cumulative distribution function. So if we sort of project them via this, and then we plot where these samples end up, basically most of them are going to appear near the, well, it's going to follow the underlying probability density function as we project them. So it will be very unlikely to get samples over here, it will be very unlikely to get samples over here. Okay, so that's how you can actually, if you can compute this, you can sample from the underlying probability density function. So now we're going to look at some of the issues in designing density estimators or designing generative models. And to do this, I'm going to use a very, very simple example, which is a histogram. A histogram is actually a classical density estimator. I'm sure you've used histograms before in Excel, in whatever spreadsheet program you've used. So a histogram helps you to estimate the likelihood over the data by dividing the space up into bins. So I'm just going to show this. So imagine we've got some space, let's just say it's a 2D space, and in that space we've got some data samples. Okay, there we go. And what a histogram density estimator does is it divides this space up into into these bins, so it's a regular grid over the space. So we've got these bins are sort of, we'll call Bj. So let's just write the equation for a histogram out. So we say the probability of the data according to the histogram density estimator is basically where we sum up for each of the bins, j equals 1 to n, and we have some proportion of our observations theta over, well, it's governed by some smoothing parameter. We have our function I, where we have the data in the bins. This should be a bold vector in the bins, bj, and our proportion theta, I'll explain this just in a sec. This is where we have our normalizing constant, but basically we're averaging within each bin. So this is, you could say I equals 1 to n for all of our data points within each bin. So basically we have this h determines the how smooth or the number of how large the bins are in covering our space, and each little x here, so we've got 3 x's, this is like xi. So as we do this, we've got this problem, which is basically is all controlled by our parameters, how much we smooth the data or fit the data. This introduces what's called the bias variance problem. So let's just imagine we've got some data here. Let's just sort of plot some data. If we set our bin size too large, we're going to have like one bin going over all of the data. So it fits really badly to it. So it's got it's got too few bins in there. So we say it's got high bias. But when you take some more data from your underlying samples, it does still fall within this bin, so it's got low variance. Whereas if you have your bin value too small, we have the same number of observations. So let's just say we've got like, and if our bins are too small now, when we plot this, we get something like this. So we perfectly fit the data, so we have very low bias. But if we then take some new samples from our underlying function, they don't fit at all to the likelihood, so it has high variance. So basically it's very sensitive to this parameter, and actually the grid function is not very good because we might have sparse data which isn't regular and doesn't fit the regular structure of a histogram, especially in higher dimensions. And similarly, we encounter this problem all the time. If you have a kernel histogram, a kernel density estimator, so you can have the probability by a kernel densification function. Again, this is kind of similar, but you would have some averaging. So this is the normalizing constant, I equals 1 to n, then 1 over our hd. This is our normalizing constant, which ensures it integrates to 1. You can imagine me writing normalizing constant 1 there. Then have our kernel function. Sorry, that should be a capital K, where we'll slide over our data. So we have a sliding window over our data set, xi, over our bandwidth, our kernel bandwidth. But basically we can choose different kernel functions in here and parameterize them. You could have like k equals to some, you could have like a boxcar kernel, which looks like this, or you could have like a Gaussian kernel, which looks like this. You could have, I think it's called an Reparameterization Trick kernel, which is like something like that, or even like a tricube kernel, which is like sharper. But there are various kernel functions you can use, and it depends on your data and how you parameterize them, but you still inevitably, how flat it is, how sharp it is, the shape of it, you end up in some sort of bias variance trade-off where you have to find the right balance. Okay, so this is a really nice example which shows this problem. So here's a distribution, a really nasty distribution, which is a good example to use if you're building a density estimator, sort of theoretically. As Nando de Freitas likes to call it, calls it the Bart-Simpson density, the one shown in red. And this distribution cannot sufficiently be estimated with a normal distribution. So the results in the blue function are the way you maximize the likelihood of mu and theta for this distribution from this probability of Bart, I suppose you could say. But it's just not enough to reconstruct the signal here. That's the best fit you can do, but it's not powerful enough to fit all of the variances in the red function, the Bart-Simpson function. So we need to parameterize much more powerful density functions. But before we get onto that, we really need to have a way to quantify if our parameterizations are good. In other words, we need to find a function that measures the distance, or more generally the divergence, between two probability distributions. And in the case of Bart here, we need a function which tells us the error between the normal distribution and this Bart-Simpson distribution. So here are two example normal distributions. What we want to do is quantify how different they are. And in this case, the standard deviations are the same between the two. So the blue function has a mean of 0, so mu is 0, and the red function has a mean of 1. So one naive thing we could do is just measure the differences between their parameters. So we could literally just take, do some L2 norm between the mu's and the sigmas. However, it's quite clear to see that the parameters may be in completely different spaces depending on how it's parameterized. So some parameters, depending on how it's parameterized, may result in very, very large changes, whereas others may result in very, very small changes to your underlying function. So we need some new divergence measure which doesn't have this sensitivity. So what we're going to use is this Kullback-Leibler divergence, and this is much more intuitive. So first of all, it's an integral, and this makes sense as you'd expect the divergence to be over some area of the error between the functions. So it's an integral of p of x. So the integral of p of x is an expected value of this function. So here we have an expected value of the logarithm of the ratio. So here's the ratio here. So the logarithm of the ratio is saying how different these two distributions are at the current point x, but doing all of that in the log scale. So what we now really have is how different these two distributions are at any data point in the log scale. And then what we're doing is we're taking an expected value of this quantity. So this has a few properties. So maybe I can just quickly jump to my notes. Okay, so first of all, you'll notice it's got that double bar notation, so it's non-symmetric. So we can say, sorry, okay. Actually, I'll just get a fresh piece of paper. So we can say that the KL divergence between P, and this means it's non-symmetric. PQ is not the same as the KL divergence between Q and P. And this is one of the reasons why it's not called a metric. It's a measure. So if you use the word metric in your writing, make sure that what you're talking about is actually a metric. So look up the definition of what a metric is on Wikipedia if you're unsure, but there's various conditions for something to be considered a metric. This is not a metric, this is a measure, because it's non-symmetric. Secondly, the distance between the same two distributions is 0. So if we have d of KL of, sorry, pencil, P and P, that's going to be equal to 0. And lastly, the KL divergence is non-negative, so we could say that the KL between P and Q is always going to be greater than or equal to 0. It's non-negative. So from a practical perspective, you can think of this really as like the surprise between the distributions. And it's particularly sensitive to the tails of the distributions. So I've got a nice example here where I've sort of coded up some of these on Desmos, so you can have a look at this. So here we are. So I've basically taken two normal distributions here, and you can actually swap them out for different distributions if you're interested in them. And I've just basically shown various measures here, so we can move the this red distribution around. We can change its standard deviation, and you can see the Kullback-Leibler divergence is very sensitive to the tails of the distribution. So as you make mistakes over here, it starts to just rapidly shoot off. Not sure if you can see that. But when the two distributions are the same, all of these measures are 0. But they have these different properties. And I'll talk about some of the others just in a minute. So these are all valid ways of assessing whether a distribution is a good fit, because all of these are 0 when they're the same, but they have different characteristics which depend on your application really. So cross-entropy is closely related to the Kullback-Leibler divergence, and we'll see it's equivalent to actually maximizing the likelihood, which we discussed earlier as actually being our goal. So basically in deep learning we may have some target distribution like a vector of zeros with say a 1 at the index of the class we're after if we're doing classification. So it's like the output neurons, you've got a 1. The target is that your predictions are all zeros for all of the other classes and a 1 at the class you're interested in, like whether it's a horse or a zebra. And then the model makes some prediction, which is just another vector. Maybe it's got some distribution now and we want to fit it to that one hot encoding, where each index corresponds to the class. And we turn this vector into a probability density function by renormalizing it such that it integrates to 1. This is where you could just ensure the network output integrates to 1 naively by renormalizing it. In practice, we use a softmax function to this, which we'll look at a lot in more detail when we actually do energy-based learning in a later lecture. But it basically, a softmax function uses an exponential to force the highest value to be near to 1, and then the rest of the values get forced closer to 0. And it does all of that in such a way that all of the values integrate to 1. But then when you've done that setup, you can use cross-entropy, which minimizes the negative log likelihood. And that's minimizing the negative log likelihood is actually the same as maximizing the likelihood to learn the optimal model parameters. So the maths here just really shows that the definition of this comes from the Kullback-Leibler divergence. But there's some extra constants which aren't really that important. They basically make the Kullback-Leibler divergence go to 0, and they're not important during optimization, so we don't actually bother computing them. So in PyTorch, if you want to estimate some distribution, you'll want to use cross-entropy, or it's called categorical cross-entropy for discrete categorical distributions, where you've got a probability mass function like in classification. So modern deep learning libraries have these functions always built into them, where some of the maths has been optimized to avoid various numerical instabilities. So you should basically not, unless you know what you're doing, write out the equations yourself. So if you want to estimate the probability of pixels being black or white, then basically what you would do is you would use binary cross-entropy. So if you wanted to learn to do a segmentation where you've got black and white pixels as your target as represented as probabilities, then use binary cross-entropy for this case. So it's like a distribution of it being white or black, or in which class it is. If you wanted to estimate the probability of an image being something like a cat, a dog, or a horse, then what you would do is you would use categorical cross-entropy. And when you use these built-in functions, pay special attention to whether the documentation says it's already got a built-in softmax on the last layer. So if it combines the softmax, or if you need to actually do your own softmax on the last layer explicitly. So some of the functions, again, they build in their own softmax to force the outputs of your neural network to be a distribution and integrate to one. And they do this to, again, save calculations later on and avoid numerical instabilities. So briefly, I'm going to just talk about optimal transport. This is a really elegant metric. So it's not a measure, it's a metric, which is like, yay, between two distributions. So this defines the optimal minimal cost of transportation between them. And this comes from this very sort of old theory, an elegant theory from mathematics, where basically you have some, the idea is you have some dirt, and you want to build a castle from all of the dirt. So you can imagine dirt as being some distribution, and then this castle-shaped function as being another distribution. And it's like the theory of how do we optimally move the dirt with the least amount of effort to build a castle. So it's very old, interesting, well-studied theory of mathematics. The least cost to the least amount of movement we need to do to move the dirt. And it defines this beautiful metric, the Wasserstein metric, where in 1D it has a closed form solution, which is basically equivalent to the absolute differences of the CDFs. But it's more difficult to work with this in higher dimensions. Yet it has several intricate but very elegant geometric characteristics that are beyond the scope of this module. In the Desmos example, I've coded it here, and you can see how the optimal transport moves very elegantly away as we move the mu parameter. But again, it's not really trivial to do it in higher dimensions. Okay, so now we've got some of the kind of foundations down, and we've got this useful armory of divergence functions. We can look at some simple deep learning architectures, and we'll be able to see their shortcomings. So let's start by restating our goal and defining generative networks. So we simply want to take some low-dimensional latent space with some prior distribution, such as this normal distribution here. And we could call this like the code distribution. But what we want to do is we want to learn to transform it by some nonlinear function, e.g. a deep neural network, such that the output satisfies x, looking like it's from the same distribution of the data distribution. X is from p data. And there's a direct solution. This can actually be solved if the latent space is of the same dimension of the data. So if we have this as the same dimensionality of the data, and also if the determinant of the Jacobian of the inverse transform of the generator function can actually be calculated, which is quite a restriction. But if we could do that, then what we could do is we could solve it for the marginals px of x directly, and you can, if you're really interested in that, you can see a derivation for it in section 19.2.1 in a video Carlin's mathematical approach book. But in practice, these two restrictions are very, very heavy restrictions. So mainly restricting our set of functions in the neural networks, you have to restrict them to be invertible functions, and that actually means we can't actually reduce the dimensionality of the data. And ideally what we want is we want a latent space that is lower dimension in a way that's representative and captures all of the high level characteristics of the data. And then we can sample new examples very intuitively. So for example, we want the dimensions of the latent space to capture semantic representations like the weather, a person's age, or the object material, happiness, and so on. We don't really want the latent space to be so high dimensional that each dimension of the components corresponds to like the individual pixel values in the data. We want to learn something of the structure of the data, the structure of the universe, learn how the rules, how all the high-level concepts combine to create the high-dimensional data. So autoencoders are amongst the simplest neural networks to implement and train, and it has an encoder network, E of x, and this basically decreases the spatial dimension of the data. And each layer in an autoencoder halves well, usually it halves the image size, or it decreases the spatial dimensions of the data. And at the same time, you generally increase the number of features or channels, so you double the feature dimensions. And then it has this decoder network, which takes this compressed representation here, and then it doubles the spatial dimensions as you go through. And each layer, basically, in the decoder, it resizes the image to be twice the input size, and then it correspondingly halves the number of feature dimensions or channels. So the final network is trained to minimize the mean squared error between the output, these predictions here, and the inputs. And there are a few simple variants to this, like denoising autoencoders. Denoising autoencoders basically partially corrupt the inputs with noise, and then at the output you get this clean output, which you basically learn to minimize the mean squared error with the clean inputs without the corruption applied. And you can also do various paired translation tasks. So you could take the inputs from one domain, so you could have like grayscale images or black and white photos, and then you can reconstruct the images from another domain so long as they're paired and aligned, such as color images. Another example of this would be to take some image of like cancer cells as your input, and then try to reconstruct some binary masks. You could use binary cross-entropy so that you have like the regions where the cancer is detected here. So I've got a collab example for this. So yeah, this is just showing the code of an autoencoder. The latent space size, or this vector here is 512 dimensions, and then the encoder just goes through the images, so it's 3 channel images, and it uses these max pool functions, which within a local 2x2 neighborhood take the maximum of it, so you get a single pixel for every 4 pixels, so it halves the spatial dimension every time you do a max pool operation. So the image goes from 32 squared to 16 squared to 8 squared to 4 squared to 2 squared, and so it's just 1 by 1. So at the end it's just a single pixel, but we increase the depth as we go through the network, so we go from 3 channels to more channels. So in this case we go from 3 channels to 16 channels to 32 channels to 64 channels, and then to 512 channels. So we've got a 512 dimensional vector at the end. And then we can just go through decoding, which is basically doing the transpose of that. Instead of max pooling, we resize the inputs to make them 2x2, and then we resize it, doubling the size to be 4x4, 8x8, and so on. And whilst we do that, we then half, or we reduce the number of feature dimensions. We go from 512 to sort of 64 to 32 to 16 to 3 again. So if we just train this, basically you'll see the outputs are quite blurry, which is to be expected. What we could do is we could increase the bandwidth. So what we could do is we could, instead of taking it all down to a 1 by 1 vector, we could sort of take it to an 8 by 8. We could have this as sort of allowing, if the inputs here are 8 by 8 in the latent space, then a lot of the signal information can actually be passed through. And when that happens, let's just do it like this. I think that's correct. Let's just test this. Yeah, you'll see this is like less blurry now and actually looks like quite sensible outputs. But basically this is actually just passing all of the information through now, so it's not actually learning much. So if we were to sample from this model, so this is sampling from the latent space with just a normal distribution, the results are not going to look very good. So let's just have a look at some samples. So this is sampling from the model, and it just looks like gibberish basically. Whereas if we sort of uncommented this, so we're squeezing it through, we look at the samples, it's a bit more kind of sensible. They look almost sensible. But it's still going to deviate over time, and this will start to look like gibberish over time. And the reason for that is that the distribution of these latents are not normally distributed. And when we were sampling from it, we were just trying to sort of draw some samples from a normal distribution and then decode those samples. But there's nothing in this architecture to say that this latent space should be normally distributed. So it would be better if we could somehow impose a normal distribution over this latent space. And that's exactly what variational autoencoders are good at, or what they do. So they have this kind of intricate little middle bit here that forces the latent space to try to follow some prior distribution. For example, they try to make it follow a Gaussian distribution, so you can sample from it. And this little trick here, or modification, can be used to make the latent space follow any type of distribution you like. It's called the Reparameterization Trick. And how it works, some textbooks like to spend entire chapters explaining this trick, but I'm just going to explain it conceptually, and if you're really fascinated by it, you can read about it. But basically, the VAE, when you train a variational autoencoder, you have these sort of the variational autoencoder loss function isn't just the mean squared error between the inputs and the outputs like in a normal autoencoder. Instead, you have like this reconstruction loss, which is basically like that mean squared error term, but you have this additional loss. So you have to balance these two losses together. And the first term here, this reconstruction loss, basically just maximizes the likelihood for each pixel. And some implementations actually use like mean squared error for this term, but most use cross-entropy. But then the second term here minimizes the Kullback-Leibler divergence between the regular autoencoder latent space and the prior. So this means that when the model is trained, you can actually sample from some random noise here, drawn from the Gaussian distribution, and you should see that the outputs look sensible. You know, even if you've got quite a high amount of bandwidth here, you should see sort of sensible looking outputs. But it doesn't mean that the outputs will look non-blurry. This is because the two objectives here actually have conflicting goals, which means that the model will try to find some equilibrium where the latent space is quite well normally distributed and the reconstructions are still okay, so they're still kind of blurry looking. Also, the fact that the reconstruction term here is, like in an autoencoder, applied pixel-wise, as with regular autoencoders. And this is actually a very poor way to model the dependencies between pixels, as in the joint distribution of the data. So one example I like to give is if I'm wearing like a checkerboard shirt, then if you move just one pixel to the left or one pixel to the right, then that reconstruction loss is going to increase drastically, even though fundamentally I'm still me, I'm still wearing a shirt. So autoregressive models do a much better job at capturing the joint distribution, so the outputs generally look very non-blurry. And this is achieved by assuming some ordering over the data, and then they factorize the joint distribution as a product of the conditional probabilities that were previously observed in a given sequence. So this works really well in language modeling tasks or in audio modeling tasks, as language and audio are both naturally sequential over time. So in the example here, we maximize the probability of the next word conditional on the previous words in a sequence. For example, the previous words may be the cat sat under, and then the model estimates the probability of the distribution over the possible tokens which follow subsequently. So where the most likely answer is, and we've given this example before, but you know, the cat sat under, we would probably get something like sensible answers with high probabilities like carpet, chair, floor, or grass. And then if you sample near the tails of that distribution that's learnt, then you would get nonsensical garbage like the cat sat on the talented, or the cat sat on the conspiracy, the cat sat on the oxygen. And it's very unlikely that you would get the cat sat on the oxygen in a given sentence. So what's really interesting, I think, is that the brain is really, really good at doing this. I can give an example. So let's just say in the context of speech recognition, how do I say, it's very easy for the brain to recognize speech. And you probably just thought I said it's very easy for the brain to recognize speech, but I didn't just say that. What I actually said was, in the context of speech recognition, it's very easy for the brain to rec a nice peach, as in the fruit. But because of all of the contextual priors, the fact that I mentioned speech recognition before, your brain was primed to interpret that sentence as recognize speech rather than rec a nice peach. Because we're basically doing this max likelihood all the time. We're given the context we're in, we estimate a probability over what we're expecting to happen, and then we fill in those gaps. Or we sample from that distribution as we model that, and we fill in the information. There's many examples of this, like you've maybe seen those examples where if you just take the first and last letter of words and scramble all of the letters between it, then you can still read a sentence even if that's occurred, just because your brain is always estimating the probability and only looking at certain things as you actually do reading. The problem with this kind of stuff is that there's no such natural ordering over space, so this doesn't really work that well with images. There are still several models that do it with images though, so they generally just assume some ordering over the pixels. So they might start in the top left pixel in an image and then slowly move along each row in the image, always maximizing the likelihood of the next pixel conditional on the previous ones it's observed. And this actually works, and you can learn a generative model for images where the outputs are very non-blurry. However, they are currently quite limited in terms of the sequence length, so they're generally not very good at doing this for very, very large images, which means that for images they often fail to capture global structure of the data. So the face may have like really nice realistic textures in it, but otherwise the eyes might be in the wrong places, so it might look like a Picasso painting. And lastly, these models can be quite slow to train, and they have some challenging issues with memory. And this kind of inherent sequential dependency makes it difficult for parallelism to occur. But there's now this massive rush of how we can get more parallelism into these kind of models. This brings us into the transformer literature, performers, and we'll see some more cool things based around this idea in the subsequent lectures. So yeah, that kind of concludes this generative models lecture. Like I said, we've just sort of laid down the foundations today, but we'll be studying a lot more in more depth generative models in the future lectures. We'll be looking at adversarial lectures, energy-based learning, and so on. All right, that's it. Thanks very much.